Hello, ladies and gentlemen. Okay, from your reaction today, I think maybe this went a little fast for you guys today. So let's slow it down and let's take a look. But that means that the responsibility is on you guys to watch this and make sure it makes sense. Sorry about that. I'm drinking my espresso as I do this. I've got about half an hour before I've got to go. And so let's see what we can do. Trig limits. So we're going, in order to determine the derivatives of trigonometric functions, we must first evaluate some special limits involving trig functions. So Adrian, that goes to what you were talking to me about. Why these trig functions? Why do I come up with sine x over x? What's going on? Well, the answer is, for me to talk about the derivative of trig functions, I need to know some special limits. And we're going to go through those, and those special limits are going to involve trig functions. So we're going to start off with the first group. The first group that I'm going to look at is just looking at sine and cosine in general. Now, I really hope that you guys are familiar with these curves, that you know that sine starts at 0, goes up to its maximum, comes back down, and continues. Sine does the same thing going in the opposite direction. I hope that you really know that at pi by 2 we hit a maximum, at pi you hit 0, at 3 pi by 2 you hit a minimum, and then you're back up to a 0 at 2 pi. Notice I'm working in radians. In this course we're going to be working an awful lot in radians, so you're going to have to be good at that. Important to note that the arguments of trigonometric functions in this unit will be expressed in radians. We will come up with degrees, we will work with degrees when we can, but understand when we're working with the limits right now, and some of the things that we do with them, we're going to have to be in radians. And I'll let you know when that occurs. It's not going to be a big deal to you guys. I'll tell you when it is. Okay, so by inspection, we can look at these graphs and we can tell. I got two graphs here. One is the sine curve, and here's the cosine curve. And I hope you understand that the cosine curve looks like this and goes on. And you should have a very good understanding that it's going to be at a maximum at 0. It hits a 0 at pi by 2, which is 90 degrees. It hits a minimum at 180 degrees. And then it comes back for 360 degrees, or otherwise known, we're going to come here, and this will be 3 pi by 2. That'll be 270 degrees. And then it'll come back up, hitting 2 pi, which is 360 degrees. So by inspection now, looking at these, just like we looked at other limits, other f of x's, these are our f of x curves. The limit as theta approaches 0, so as I approach 0 from the left, and as I approach 0 from the right, you'll notice that both limits are approaching 0. So the limit as x approaches 0 of sine theta not only exists, but it equals 0. The limit as theta approaches pi by 2. So as theta approaches pi by 2, so getting closer and closer to pi by 2, the range value is going up and up and up to 0. As I approach pi by 2 from the right-hand side, it's going up and up and up to 0. And so they're both approaching the same value. Okay? So therefore, we say that the limit exists and it equals 1. As I'm approaching negative pi, way out here, negative pi. So as I approach from the left, I'm coming down and down and down to 0. As I approach from the right, I'm coming up and up and up and up to 0. Therefore, the limit exists and it equals 0. Same thing with cosine. The limit as theta approaches 0 for cosine, coming in from the right and coming in from the left, you'll notice that the range values are both approaching 1. Therefore, the limit from the left, the limit as theta approaches 0 from the right, of cos theta equals 1. The limit as theta approaches 0 from the left of cos theta equals 1. Therefore, the limit exists and it equals 1, which is basically what we're saying here. So we're going to have to keep these in mind. Okay, we're going to use these later on, and we're going to have to be able to come up with those answers by thinking about them, not drawing the graphs, but thinking a little bit about them and knowing what's going on. We will be able to think about this as theta approaching 90 degrees. That'll work out just fine. Theta approaching negative 180 degrees. Theta approaching 90 degrees again. and theta approaching negative 180 degrees. We can think about it that way at certain times. It's only when we are really working with the limit charts that we have to worry about the radians. Special triangles, you need to know, this should be something that you know already. Pi by 6, you should know that that's 180 degrees divided by 6. So I'm really hoping everyone's on board with 30 degrees. And pi by 3 is 180 divided by 3, so that's 60 degrees. And again, I expect you to know this. This is knowledge that you're supposed to have. Notice the side lengths. 1, 2, square root 3. The largest of those is 2, so it's opposite the largest angle. The smallest of those is 1, so it's opposite the smallest angle. And the one in the middle is root 3, and it's opposite the angle that's between 30 and 90. 60 is in between those two. And we get 1, 1, root 2 for a 45, 45 degree triangle. 45, 45, 90, sorry. And that's what we come up with. And don't be afraid to rationalize denominators. So even though the cosine as theta approaches pi by 4, so this is the limit. As theta is approaching 45 degrees of cosine, it's going to be adjacent over hypotenuse, so 1 over root 2, but we rationalize the denominator, and we're going to get an answer of root 2 over 2. Over here, the limit as theta approaches pi by 3, so that's as theta approaches 60. So we go to our 60, 30, 90 triangle. We find the angle that's 60. Here it is, pi by 3, and it's sine, so it's opposite over hypotenuse. So it's root 3 over 2, and there you go. Flipping over. All right, now, the most important trig function that we have to know about, the most important for you guys in this course is this one. Adrian, I can hear you yelling at me, but why? Because I'm going to use it for the derivative proofs. So that's why. I need this one, and I need one other one to be able to do derivative proofs with you. So sine x over x is a function. Adrian was quite right. What does it look like? What do we think? You go and plug that into Desmoth graph. The actual curve of, go graph sine x over x. You're going to see that it's a smooth and continuous function, and take a look at it. It's interesting. But what I'm interested in, the limit of sine x over x. Why? Because that's going to show up when I try to do a derivation proof. Now, notice, if we try to evaluate this limit directly, as x approaches 0 of sine x, we're going to remember that the derivative of, that the limit of sine x as we approach 0, so from left and right is 0, so the top's going to be 0. The limit as x approaches 0, 0, we're going to end up with the indeterminate form. So we need to do something more, okay? That's not good enough. We've got to do some work. So we're going to go and do the most basic thing that can ever be used for evaluating limits. It's a chart, okay? However, this and only this is when you have to remember to use radians, okay? When we're doing a limit chart, we must be in radians. So I'm looking for my calculator. All calculators are different. Mine says hit mode and then hit 5, and I switched into radian mode. What I'm going to do is I'm going to take these values now, and I'm going to plug them in here. So 0.01, 0.1 negative sine, that's in radians, divided by 0.1 negative equals 0.9983 yada yada yada. Next one, 0.01 negative, notice I'm still in radians, that's a radian, sine divided by 0.01 negative equals. And I have to be honest with you, it's not terribly important that you can do this. So 0.001 negative sine divided by 0.001 negative equals, how many are there? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And as we can see, at least I hope that we can see, that this is approaching and getting closer and closer to 1 full radian. Okay? So that's going to equal 1. And this is definitely the limit as x approaches 0 from the left. because these are values that are less than 0. Now, if I do the exact same thing with values that are to the right-hand side of 0, greater than 0, what you're going to come up with are these values. There's a certain symmetry here. Six of them. And I think we know that that's approaching 0. So if the limit from the left is approaching 1, and the limit from the right is also approaching 1, then we know the limit as x approaches 0 exists, and it too will equal what the two others equal. So what am I saying? I'm saying that this result is very important to our future. We need to know that. Do I need you to be able to find this? Not so much. Did I prove it to you? I hope so, and I hope it makes sense where it came from. It might not make sense why we have to be in radians. On another day, I might go into that a little bit more, but let's put it this way. It has something to do with the rotational angles and the fact that they keep doubling over, whereas radians are a number of radians, and they can't double over. So many radians equal that many radians. Again, I know that's a little fuzzy. You don't really need to know that much about it. What you need to know is this. I'm going to pause here for a minute.